Bismillahirrahmanirrahim. So this is our lecture number 7, and in this lecture we are going to discuss another very important module of microcontrollers, which is timers or counters. And I also tend to call it a frequency divider for the reasons that I'm going to discuss shortly. So this is one of the very most important kind of components within the microcontroller, as it is used to help many other devices also complete their functionality. So in this lecture, we are going to see how does it function, what is its architecture, and what are the different modes in which it can work. So ATmega 3288P is equipped with 3 timers or counters. So for the sake of simplicity, I'll just call it a timer. So there are two 8-bit timers which count from 0 to 255. These are timer 0 and timer 2. And there is one 16-bit timer which is counts from 0 to 65535. Obviously, this is the 2 raised to the power 16, and this is timer 1. Now, internal functionality of these timers is almost the same with very minor difference. So we are going to cover one only timer 0, and you can then extend your knowledge beyond that to timer 1 or timer 2. So as it is obvious that timer 1 is used when you want larger delays, or you want to count large number of events more than 255. So what are the functions that these timers allow you to perform? So first of all, turn on or turn off an external device at a programmed time. So you can count the certain amount of time, and after that you can go do some internal housekeeping, some external work, and start the functionality again. Then you can generate a precision output signal with specific period, duty cycle, or frequency. For example, you can generate pulse width modulated signals for speed control of a DC motor. Then you can measure these same characteristics, period, duty cycle, and frequency of an incoming digital signal. And finally, you can count the external event. Now, once you write this function delay x, where x is the amount of delay that you want to give in the execution of your program, x is in milliseconds usually. So what it does is that it actually calls or uses the timer or counter to count enough number of times which causes this much amount of delay in milliseconds. So let's discuss the architecture of a 4-bit timer, counter, or frequency divider, which is equivalent terminology for this kind of a circuit. So a timer actually consists of a T-type flip-flop, sometimes also a JK flip-flop. Now a JK flip-flop or a T-type flip-flop in the toggle mode. So the T-type flip-flop has the characteristic that once its input is fixed tied to 1, or its input is whenever 1, and it receives a clock signal, then it toggles its output. If earlier it was 0, it goes to 1, and if it was 1, then it goes to 0. So now in this circuit, we are shown 4 T-type flip-flops which are cascaded with one another. The output of one drives the other. So we start from the leftmost T-type flip-flop. So here we have our first T-type flip-flop. We see that its input is continuously tied to 1. Whereas the next T-type flip-flop, its input is being driven by the output of the previous stage. So the output of the first flip-flop is called Q0, which is also LSB. Then the output of the first flip-flop is Q1, and Q1 and Q0, they are driving the third flip-flop, and then its output is Q2, and then the Q0, Q1, and Q2 combined, they're driving the fourth flip-flop. Or you could say this is flip-flop 0, flip-flop 1, flip-flop 2, and finally the flip-flop 3. And you correspondingly have the outputs designated with them as Q0, Q1, Q2, and Q3. Now, you also see a clock signal because they are synchronous sequential circuits. So, flip-flops are synchronous sequential circuits. They operate only on the arrival of the clock signal and exactly at the edge of the clock. Either the positive edge, which is going from low to high, or the negative edge, which is going from high to low. They actually sample the input and then they perform their function and give you the output. So now here we have a small circle at the input of the clock signal for the flip-flop. So this means that this is a negative edge triggered device, which means it is going to sample the input at the negative going edge of the clock. So you could also make it positive edge, that doesn't make any difference. So let's see what will happen. So this is the output Q0, this is Q1, this is Q2, this is Q3, and this is your clock, and we are shown 10 clock cycles. Okay, so at the first negative edge or the first negative clock edge, the flip-flop 0, now flip-flop 0 samples its input and it finds that its input is equal to 1. So as a result, what it does is it toggles its output from 0 to 1. So the assumption is that initially all the flip-flops are at 0. So it goes from 0 to 1. Now the next half cycle, clock cycle comes, the transition from low to high occurs, but nothing happens because the flip-flop is designed to work on the negative clock edge. So at the next negative clock edge, what it sees is that there is again the input 1. So it toggles its output again. And it goes from 1 to 0. Then again the positive clock cycle, positive edge of the clock passes without any transition. At the negative edge again, you see that since again the input is 1, there is again a transition from 0 to 1. So the first flip-flop at every negative clock edge or every high to low transition, its output keeps toggling. Now, you see that in a way, it looks that it is dividing the input clock by 2. So it is perform. You can, depending upon your type of application, you could designate it in 3 different ways. First of all, it could be counting the number of clock edges, which is going to become clear once we have discussed Q0, Q1, Q2, and Q3, all of them. Then it could also be that it is dividing the frequency. If you look at the clock and output of Q0, you see that the frequency of Q0 is half the input clock frequency. So you could say that the FQ0 is equal to clock divided by 2. So our claim is, which we are going to see once we discuss the flip-flop 1, that at every next cascaded stage, the frequency gets divided by 2. So I am saying that the output frequency of FQ1 will become equal to clock divided by 4, because the input clock it will be getting will be at the rate of this output. Let's see how that happens. Okay, so now we get to flip-flop 1. So flip-flop 1 has input from the output of flip-flop 0. Okay, so the first negative edge of the clock cycle comes. Now, once this negative edge of the clock cycle comes, the flip-flop 0 makes a transition because its input was already set at 1. However, due to this delay in the transition, at this very moment, once the input of flip-flop 1 is sampled, it was at this point 0. Now the time it takes actually to transition from 0 to 1, during this interval it is considered at 0. So, or you could otherwise say that just before the negative edge of the clock, what was the input at the at the flip-flop 1. So just before that it was 0, so it doesn't make a transition. Now at the next negative clock edge, so just before the negative clock edge, the input to flip-flop 1 is 1. So since this input is 1, this obviously makes a transition and goes from low to high. Again, next time at the negative clock edge, once the input is sampled just before this negative clock edge, you see that it is 0. So flip-flop 1 doesn't make a transition. It continues at 1. Then at the next negative clock edge, which is for the 4th clock cycle, you see that just before this negative clock edge, once the input flip-flop 1 is sampled, this is equal to 1. And that is why it makes a transition from 1 to 0. And then it moves on at the negative edge of the 5th clock cycle. The input is sampled just before that, which is 0. So you see that because of that, there is no transition in the flip-flop 1. It continues in the similar manner. And at the negative clock edge of the clock 6, again, once the input is sampled, you see that at that moment it is 1, and that is why flip-flop 1 output makes a transition from 0 to 1. So at every negative edge of the even numbered clock cycle, it is making a transition, while at odd number it is staying at the same place. Now if you measure the frequency of Q1, it is clearly half the frequency of Q0, which is half the frequency of the input clock. So that means that the output clock of flip-flop 1 is obviously the input clock divided by 4. Now we repeat the same argument to Q0, Q2, and which is flip-flop 2. So the flip-flop 2 is being driven by the AND of Q0 and Q1. Now it means that it is going to receive input 1 only once both Q0 and Q1 are 1, otherwise it is going to remain 0. So we mark the negative edges of the clock cycles and we see where both Q0 and Q1 are 1. Okay. So at this clock edge, obviously just before this negative edge, Q0 is 0, Q1 is 0, nothing happens. At the second negative edge, just before that, Q0 is 1, but Q1 is 0. At the third, you have Q0 as 0 and Q1 as 1. At fourth clock edge, exactly before the edge, you have both Q0 as 1 and Q1 also as 1. And that is why Q2 makes the transition from 0 to 1. Then at the fifth, you have both equal to 0. At the sixth, you have Q0 as 1, but Q1 as 0. At the seventh, you have Q0 as 0, but Q1 is 1. And again at the eighth, you have Q0 as 1 and Q1 also as 1. And that is why it makes a transition from high to low. So now you see that one clock cycle of Q2 accommodates 8 clock cycles of the input. 8 clock cycles of the input. Or it accommodates, again, 1 clock cycle of Q2 accommodates 2 clock cycles of Q1. Q1 accommodates 2 clock cycles of Q0. Q0 accommodates 2 clock cycles of the input. So that means at every stage, the frequency is getting divided by 2. So FQ2 is equal to clock divided by 8. Okay, so you can continue with the same argument for the flip-flop 3, just by considering that it is driven by the AND input from Q0, Q1 and Q2, which means that its input is going to be 1 only once all of Q0, Q1 and Q2 are 1. Okay, so by that you can actually verify that this waveform is correct. Now important thing is, let's just give them numbers 0, 0, 0, 0, then you have 0, 0, 0, 1, then you have 0, 0, 1, 0, then you have 0, 0, 1, 1, and then you have 0, 1, 0, 0, and then 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, and then you have 1, 0, 0, 0. So if you have their binary equivalents, then their decimal equivalents, then this is 0, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, this is 8. And now you see that this number is actually equal to the number of clock cycles over here. So in a way, what it is doing is that it is counting the number of clocks that it has received at the input. So first we have seen that it is acting as a frequency divider, and it divides the frequency by the number of stages it has. So every stage divides the previous frequency by 2. So you could divide it by 2, you could divide it by 4, you could divide it by 8, and here you could get a frequency which is divided by 60. Then the second thing it is doing is it is counting the number of events or the number of clock pulses it has received. So for this case, we have given the clock signal as a continuous stream of pulses which has 50% duty cycle and a constant frequency. However, if these were, let's say, pulses received from our autoencoder or shaft encoder mounted on our DC motor. So depending upon the speed, you could be getting your pulses like, let's say, this. Now it is going to count every negative edge of the clock, right? So if we see that, then the output of this complete circuit will become 0, 0, 0, 1. So here it will become 0, 0, 0, 1. Here it becomes 0, 0, 1, 0. At this negative transition, it will become 0, 0, 0, 0, 1, 1. At this negative transition, it will become 0, 1, 0. So it is counting the number of events that have occurred and it has received. So two things, and then finally its function as a timer. So we know that by giving it a specific clock frequency. So suppose that we are giving it a clock which is suppose the clock signal given to it is 1 hertz. So that means that every pulse has a time period equal to 1 second. Now suppose we want to wait, or we want to check certain peripheral, or we want to perform some specific function after, let's say, 13 seconds. So what should we do? All we need to do is now give it this clock and count the number of pulses till 13. And once 13 pulses have been counted, it would mean that 13 seconds have passed. And at that point, what we do is we just do the action we want to perform through some interrupt, through some code. So that means that once a certain count is completed, at that point, we can raise an interrupt, and that interrupt is going to do what? So that interrupt is going to actually tell us that our time delay has completed, right? So usually the clocks are in megahertz, and the time is in microseconds. Then it is first of all divided by a prescaler. The clock is divided by a prescaler to make it a bit slow, so to give us a reasonable time delay, right? So within the interrupt, then what you could do is you could again reset the timer to 0 so that it again counts 13 number of events, and within the interrupt you could perform whatever functionality you wanted to perform. So this is how the timers actually work. There are many circuits and they're all equivalent. You could find implementations with JK flip-flops. There are some certain other implementations as well. So timing terminology, frequency, obviously the input clock frequency that is being given to the timer, period, the time period, duty cycle. So duty cycle is, so as we have said, the timers or counters can also be used to generate the a specific kind of a pulse width modulated signal. So the percentage of time with percentage of time in a clock cycle for which the output remains high is called duty cycle. So suppose this time is tau, this complete time is t, then your duty cycle is equal to tau over t times 100. Now what is its effect? The effect is that suppose you are trying to drive an LED, so you give it such kind of signal which has suppose a duty cycle of 25%. So the low of this pulse is 0, the high is 5 volts. So the effect of this is that if you give such kind of signal to this LED and the other end is grounded, then it is receiving the energy, electrical energy only for 25% of the time. So in terms of voltage, we could say that it is receiving 25% of the peak voltage. So V is equal to 25% of 5 volts. So we could say that it is receiving 1.25 volts on average. So the average impact is 1.25 volts. The instantaneous impact is still 5 volts, which means that once you drive this LED, obviously it doesn't mean that it is going during this period it is going to receive 1.25 volts. During this period it is going to receive complete 5 volts. However, if you average it out over this complete time period of the pulse, it is on the average, its impact will be equal to 1.250, or the electrical energy transferred to this complete to this LED will be the effect of 1.25 volts. The next thing is the resolution. So generally the bit width, as I said, the number of T-type flip-flops within cascaded within the timer, they are used to determine the bit width of the timer. So for example, in the previous case we had the 4-bit timer. If you want an 8-bit timer, we will have 8 flip-flops cascaded in the similar fashion, right? So if we need a 16-bit flip-flop, so it will have 16 such T-type flip-flops cascaded together. Now, what is the important thing over here? The important thing over here is the resolution. So sometimes the resolution is the minimum amount of time that a timer can measure. So minimum amount of time a timer can measure. So that obviously should be equal to 1 clock cycle. So because in 1 clock cycle, it is going to transition from 0 to 1. So if your clock is, let's say, F clock, then your resolution is 1 over F clock, which means it is actually making a transition. Its output is making a transition every 1 over F clock seconds. So like I said, suppose you have a timer which is being given input at 1 kilohertz. So its resolution will be equal to 1 over 10 to the power 3 is equal to 1 millisecond, which means it is going to transition every 1 millisecond if you are giving it a constant stream of pulses. Obviously, if you are counting the number of events and they are coming at a different frequency, that would mean something different. So sometimes the bit width is also used to define the resolution, and but however, this is the correct definition. The time it takes for the timer to make one transition. So as I said, we are going to discuss only timer 0. So let's see what it can do. So we already know it is an 8-bit timer, which means it can count from 0 to 255. It can count maximum of 256 input pulses. So it has a single compare unit. Let's see what does that mean. Clear timer on compare match, which is auto reload. So whenever the comparison is made, which means that the required number of pulses has been counted, then automatically the timer is can be reset. Glitch free phase correct pulse width modulator. So it has a pulse width modulator. It can be used as a frequency generator. So as I said, every timer or counter can be used as a frequency generator of different, so it can divide the input frequency by 1, by 2, 4, 8, and even other combinations can be made by suitably combining the outputs of the timer. Then it has 10-bit clock prescaler. So you can divide the frequency, input frequency to the counter by or timer by 1, 8, 64, 256 or 1024. So this is just to increase the time period of the frequency, the clock being given to the timer as the input. So what it is going to do is it is going to allow us to play with the larger delays. So for example, you give it a frequency of 1 megahertz. That means its resolution is only 1 microsecond. So only in 255 microsecond it is going to roll over. So now suppose if you want to count maybe 4 microsecond, not 4, but let's say 1 millisecond. Then in order to count 1 millisecond, you need to use a timer which has enough number of bits installed in it. So this 8-bit timer cannot be used because it can only count till 255 microseconds, and after that it rolls over. So instead what you could do is you could slow its clock. So if you divide its clock by 8, so that means that its timing is going to change. Instead of 1 microsecond to 0.12 in fact 8 microseconds. So that means now if you count only up to 125, so by counting up to 125, you will have a time delay of 1 millisecond. So that is why the clock prescalers are used. They are used to slow down the input clock so you could manage the larger delays. Then it has overflow and compare match interrupt services. So if it overflows, which means that you want it to count and go to the end, so once it reaches the end, it overflows and starts back from 0. This condition is called overflow, and you want that there should be an interrupt once that happens, so that you could take some action. So it has that capability. Then compare match interrupt sources. So that means that instead of fully going from 0 to 255, suppose your application dictates that your time delay will be over once it has counted only up to 200. So you have that capability that once it has counted up to 200, so in that case, it is going to generate an interrupt once the count to 200 is complete. So it has two different types of interrupt. One is the overflow, the other is the output compare or the compare match interrupt. So this is the block diagram of the 8-bit timer or counter. So let's just see how does it function. So first of all, you should understand that n is equal to 0 represents the timer counter number. So if n is 0, this means we are talking about timer 0. X is equal to A or B represents that the output compare units A or B. So same timer could actually be used to track two different counts. So for example, you have to take some action once the count is equal to 100, and then you have to take another action once the count is 220. Then the same timer unit allows you to track up to two counts. and that is why it is called count A or count B. So let's see how it functions. So here you have the timer 0 event or clock. So if you are counting number of events, you will be giving it externally. And if you are just utilizing the internal clock, which is driving the microcontroller, you could drive it through the pre-scaler. Okay, so now the clock select actually tells which of these is going to go forward and drive the control logic. So this makes the clock of the timer 0. Now you have a clock control logic over here. So if you have a timer overflow, so so this actually keeps counting, and if you have a timer overflow, then this generates the timer overflow interrupt. Then here you have the direction signal. Direction tells whether you want the counter to count up or count down. So there are up counters and down counters. So the up counters increment where the down counters decrement. So you have a clear signal. The clear signal actually clears the total count up to which the timer has already counted. So for example, it has counted up to 88 and you give the clear signal, it will reset to 00, all zeros. And then the count. So this is the signal which actually takes the counter forward. So this is the timer counter register. And then here you have the compare register. So what is happening? So the counter, so the count signal is coming over here, the timer is counting, and if you just want it to overflow, then this overflow interrupt is going to be generated from the control logic. However, if you want to count up to a certain number, then you need to store first of all that number into some register. So that number is stored in output compare register A or output compare register B. So suppose you stored 100 over here, a 220 over here. So you see that the counter output is coming to this comparator. So it is going to count if the comparison up to, if it has already counted up to 100, then it is going to give its signal at two outputs. One is output compare A for interrupt purposes or to the waveform generator signal. So to the waveform generator module, which is used to generate the PWM output. And it again goes to drive this also. And what it does is that it actually then rolls over the timer for the count for so this signal over here, this top, we are going to shortly define this top and bottom. So bottom is the lower value, the lowermost value from which you start counting, and top is the maximum value up to which you count. So you can actually the bottom is at 0, but the top you can also define it through this output control register, that what is the maximum value up to which you want to count. Okay, so that same timer output, it comes over here to this other comparator module as well. So here you stored that you want to count up to 220. So the count is coming over here. It gets compared. If the comparison is okay, then you have the output compare interrupt request generated from over here, or you can drive the other PWM signal, which is given at the output compare port B and output compare port A. So this is how the timer actually functions. So these are the definitions as we were discussing. Bottom, the counter reaches the bottom when it becomes 0, 0. So bottom is always 0, 0. Max, the counter reaches its maximum value which it can count, which is 0 cross FF or 255. Top, the counter reaches the top when it becomes equal to the highest value in the count sequence. The top value can be assigned to be a fixed value which is equal to max, or the value stored in the OCR 0 register. So what you could do is that you can alter. So actually the timer is designed to count from 0 up to 255. However, you can make it a timer which can count from 0 up to some value x. This x could be 100, this could be 200, this could be 133, whatever. So you have this flexibility. Now, what are the modes in which the timer functions? One is the normal mode in which it just increments. Then it is the clear timer on compare match, in which case once the match has occurred, it clears the timer and restarts again. Then it has the fast PWM, single slope PWM mode, and then it has the phase correct or PWM, which is also called the double slope PWM mode. So let's see them in detail now. So these are the important registers within the timers. So first of all, you have the timer count register. So this is actually the one which is keeping track of up to what has been counted. So this is the actual counter. Then timer overflow flag, which tells that the overflow has occurred, so generate an interrupt. Then timer counter control register. So the control register is where you set different modes of this timer. Then output compare register. So this is where you put the values to which you want to compare whether the timer has counted up to this point or not. And then output compare match flag. So this is flag is raised once the output compare the comparison between the timer and the value that you had set in OCRN has occurred. And then you have timer interrupt flag register, which is raised once a timer interrupt has occurred. So this is a bit of detail of the registers. So first of all, you have the timer counter and output compare these are 8-bit registers, right? So obviously this has to count, this is an 8-bit counter. So this has to be 8-bit, and then this has to store an 8-bit value which will be compared to the timer counter. Interrupt request is the signals are all visible in the timer interrupt flag register. All interrupts are individually masked with the timer interrupt mask register. So the type of interrupt that you want to enable, that will be enabled in the timer interrupt mask register. The timer interrupt flag register and mask are not shown in the figure since these registers are shared by other timer units as well. The timer or counter can be clocked internally via a prescaler or by an external clock source on the T0 pin. So this we have already seen. The clock select logic block controls which clock source and edge the timer counter uses to increment or decrement its value. Then the timer or counter is inactive when no clock source is selected. The output from clock select logic is referred to as the timer clock, right? So it is clock T0. The double buffered output compare register is compared with the timer counter value at all times. The result of the compare can be used by the waveform generator to generate a PWM or the variable frequency output on the output compare pin, right? So this is something that that we can do. The compare match event will also set the compare flag, which can be used to generate an output compare interrupt request. So this is also something that we have seen in the block diagram. Now, this is the timer counter control register. So what all does it have? So you see that it is an 8-bit register and it has pins CS000102. So these are 3 pins performing some function. Let's see that. Then you have WGM01 and then you have COM0001 and here you have WGM00 and here you have FOC0. Now this is only for writing, these are for reading, writing, and all other pins are read-write pins. Initial values are all 0 whenever the microcontroller is reset. So FOC0 is the force output compare. So it is only active when WGM0 bit specifies a non-PWM mode. So once you are in the non-PWM mode, then it is active. However, for ensuring compatibility with future devices, this bit must be set to 0 when TCCR are 0 is written when operating in PWM mode. So it has to be 0 whenever you are in PWM mode. And when writing a logical 1 to this bit, an immediate compare match is forced on the waveform generator unit. So if you write 1 to it, the impact is that no matter what the timer is doing, immediately the waveform generator unit is going to force a compare match and generate the event. So suppose your counter is counting from 0 and going up to this value. So I'm showing this as 0, 1, 2, 3. So just consider them as steps. And here is 255. And just that suppose it has counted up to 99 and you make this pin FOC 0 as 1. So if you make this as 1, this signal is going to mimic that as if your comparison has already occurred, and because of that it is going to force it to come down to 0 and start counting again. And at this point, this is registered, and here if you want to take some action, you can take some action. So this is actually given you as a capability that if you don't want to count all the way up to the compare value that you have given in under certain circumstances, then just by forcing this pin to be equal to 1, you can ensure that the timer resets. So we see that what is going to happen once FOC 0 bit is set to 1, it all depends upon this configuration of the COM0 compare 0. 0 stands for this register, bits 0 and 1 that we have already seen in this register. So so these two pins, they are going to actually decide what is going to happen once this is 1. So these modes are discussed later. And then this strobe, it actually doesn't generate any interrupt, or it does not clear timer once it is in the once it is in the compare timing timer mode. Okay, so these are the pins, bits number 3 and 6, which is waveform generation mode 0 and 1. So once these pins, they are 0, 0, so you are in the normal mode, which means you are just counting as a normal counter. It acts as a up or down counter. If it is 0, 1, then it is in the PWM phase correct mode. If it is 1, 0, then it is in the CTC mode, which is clear timer on compare match mode. And then if it is 1, 1, then you are in the fast PWM mode. So these modes we are going to discuss shortly. Right now we are discussing just the registers. Now in this case, the value of top is going up to the max value, and the overflow flag is set once the timer reaches its maximum. Similarly, in PWM phase correct mode, the top value is 0 cross FF, and fast PWM also it is 0 cross FF. However, in the clear timer compare match mode, the top value is set by OCR0, which is the output compare register 0. So this is the highest point up to which the timer is going to count, and then it is going to reset. Okay, now talking about the pins bit number 4 and 5, which is COM0 bits 0 and 1. So these are compare match output mode. So if they are 0, 0, you are in normal operation. If you are 0, 1, then toggle OC0 on compare match. So this is the output compare 0 pin. So if it was 1, just toggle it to 0. If it was 0, then toggle it to 1. So if it is 1, 0, then clear output compare on compare match. So the pin is cleared, which means if it was 1, clear it to 0. And 1, 1, now in this case, set OC0, which means that earlier on, as long as the match has not occurred, it will be going to 0, and then it switches to 1 as the comparison occurs. So let me show you this OC0 pin again, where it lies. So this is where you have it. Output compare 0A or output compare 0B. Right now, the last 3 pins, which is CS0, clock select 0 to 2. So we have seen that you could select the clock from 2 sources, either an external or an internal with the prescaler. So these 3 bits determine what is going to happen with the input clock. So if it is all zeros, then there is no clock source, and it means the timer is in the hibernate mode. It's not doing anything. If it is 001, then it is in the from 001 up to 101. So these are 1, 2, 3, 4, 5. So 5 modes in which the input to the counter is given from the prescaler. And this is with no prescaling, prescaling divided by 8, divided by 64, divided by 256, and then divided by 1024. Then the next clock, the next is 110. And if the input, if these pins are configured as 110, then the external clock source on T0 pin will be utilized to drive the timer. However, the transition is going to take place on the falling edge or the negative edge. And then you have 111. So in the if the pins are the bits are configured as 111, then again external clock source given on T0 pin will be utilized, but the transitions are going to take place on. So now we also have the two bits, which is COM01 and COM00. So they are actually used to determine what happens to the output compare pin once we are in the PWM mode. So as we said, there are 2 PWM modes. One is called fast PWM, the other is called phase correct PWM. So in the fast PWM, once these pins are 00, it means a normal port operation. So actually OC0 is disconnected. In 01 is reserved. 10 is clear OC0 on compare match and set OC0 at the bottom, right? So what happens is that if your counter is going up and up and up, and so here it is 0, 0, it is 255 over here, and a comparison occurs at this point, then at the comparison it is going to clear OC0. And once it reaches 0, let's say like this, or whenever OC0, whenever this timer is at the bottom, then it sets OC0. So it is going to be a signal somewhat like this. So this is called the non-inverting mode, and then the opposite is once you have COM01 and COM00 set to 11, then the pin OC0 is set on the compare match, and it is cleared at the bottom. So this is the reverse. So at the comparison, it is going to go high, and then once it reaches the bottom, the timer is set to bottom, then it is going to get back to 0. So this is how it is functioning. In the phase correct mode, then the PWM mode is changed. 00 is again for normal operation, 01 is reserved. 10 again, it clears OC0 on compare match, 1 up counting, and set OC0 on compare match, 1 down counting. So basically, the difference between fast PWM and phase correct PWM is something that we are going to see in the next slides. But the fast PWM relies only on up counting, whereas phase correct PWM counting relies on down counting as well. So it counts from 0 to 255 and at the maximum it starts to count from 255 to 0. So this is how its counting looks like. Now once the comparison occurs, so if it is up counting, then OC0 is cleared, and once it is down counting, then OC0 is set to 1 once the pins are 1 0. And the opposite occurs when COM0 0 and COM0 1 pins are 1 1. Then you have the timer counter interrupt mask register. So here you have again 8 pins, and you have, let's say, bit 0 timer counter overflow interrupt enable. So this is used to enable the interrupt. Then timer counter 0 output compare match interrupt. So if you want to enable the output compare match interrupt, this is enabled from bit 1. Then you have the timer counter interrupt flag register. Again, you have the bit 0 as the timer overflow flag. So this represents that in the normal mode of operation, the timer has overflowed, and in the bit 1 is output compare flag, which means that in the normal mode of operation, the OCF0 bit is set 1 when the compare match occurs between the timer counter and the data in OCR0 register, right? So once the timer output and the amount up to which you want to count it, they become equal, then this flag is set to 1, and this actually tells that the interrupt has occurred. Let's now talk about modes of operation, which is going to conclude this lecture. So first is the normal mode, and in this mode of operation, basically what you do is you count from 0 up to a maximum value, or from a maximum value to the bottom value, and that's how the timer works. So basically, the mode is defined by the combination of the waveform generation mode bits and the compare output mode bits in the timer counter control registers A and B. The compare output mode bits do not affect the counting sequence, while the waveform generation mode bits, they do affect the counting sequence. And then COM0 bits 0 to 1, they control whether the PWM output generated should be inverted or non-inverted, which is in the fast PWM mode. And for non-PWM modes, COM0x01 bits control whether the output should be set, cleared, or toggled at a compare match. So this is something that we are going to see right now. So in the normal mode, this is the simplest mode of operation. And in this case, the waveform generation mode pins 0 to 1, 2, they are set to all zeros. In this mode, the counting direction is always up incrementing, and no counter clear is performed. So there is no need to perform the counter clear, because it is going to count from 0 up to the maximum value, and then it is going to reset. So, and then it is going to restart counting from the bottom. In the normal operation, timer counter overflow flag will be set in the same timer clock cycle as the timer counter interrupt becomes 0. So as soon as the timer rolls over from its top to the bottom, then the timer overflow flag is going to be set in the same clock cycle. The timer overflow flag 0 in this case behaves like a 9th bit, except that it is only set, not cleared. However, combined with the timer overflow interrupt, that automatically is the TOV0 flag. So here you can generate, you can combine it with the timer overflow interrupt, which automatically clears this flag. Then the clear timer on compare match mode, CTC mode. So it would have been better if they had written it as CTCM mode for the sake of completeness. So in this mode, CTC mode, the pins which are the waveform generator mode pins. So W is missing over here, that you can put yourself. So this is set to 0 cross 2, which is 0, 0, 1, 0. The OCR register is used to manipulate the counter resolution because this determines when the counter is going to roll over. In the CTC mode, the counter is cleared to 0 when the counter matches the OCR value. So on one side you have the timer counter register. So this is TC and T0. On one side you have OCR 0, and here also we saw that there are two registers in some cases, OCR 0A and OCR 0B, and here you have the comparator. So it is receiving the input from both, and as soon as the comparison is made, then it resets the counter. So it gives the reset counter signal. Now, the OCR 0 defines the top value for the counter because this is the maximum up to which the counter is going to go, and therefore also its resolution, that this is the maximum it can count. This mode allows greater control of compare match output frequency. It also simplifies the operation of counting external events. So you see that. So suppose this is how your timer is counting from 0 up to 255. So at this value, your rollover occurs. It gets from 255 to 0, and this is how it is functioning in the normal mode of operation. Now, what you could do is, instead of 255, you could set another value which is called top. So suppose you want it to roll over at 200. So whenever the counter is going to reach T200, the output compare interrupt flag is going to be set, and the counter will go back to 0 and start counting again, and then it is doing like this. And suppose now while your system is operating, you change the output compare register value. So now instead of 200, you want to roll it over at 170. So it is going to roll over at 170. Suppose in the next phase, you want to roll it over to 150. It is going to roll over at 150, and so on and so forth. So now you see that the output is going to be generated like this. So it is going to be set to 1 once your you have your top is your counter reaches the top value, and then it is going to remain at 1. Then next time it reaches the top value, it is going to toggle, get back to 0, and then again once it reaches the top value, it toggles. So this toggles like this. So you see that the output compare register, this actually also affects your output frequency, right? So here the frequency is lower, here the frequency is higher, and that is why it affects the resolution of the output of the timer as well. Now, for generating a waveform output in CTC mode, the output compare 0A output can be set to toggle its logical value on each compare match by writing the least significant bits compare output mode bits in the timer counter control register, right? So actually what we have done, this is actually the description of what we have seen over here. So what you are doing is that you are counting from 0 to top. So whenever you are going to change the top value, obviously it is going to go up to that point, and it is going to give you an output of varying frequency. So this is set using these two registers, the timer counter control register A and its pins COM 0, 1, 0, and 1. So these bits. So the output compare 0 A, which is for the A module of the output compare. So this this value will only be visible on the port pins unless the data direction of the pin is set to output. Now the waveform generated will have a maximum frequency of F oscillator 0, which is equal to the input output clock divided by 2, and the waveform frequency is generally defined like this. So n represents the prescaler factor. So it is, if it is being run by the internal clock, then the input clock divided by 2 and multiplied by n, 1 plus OCR and x. So output compare register value plus 1 times the prescaler factor and 2. So this is in the denominator. So this is the maximum the waveform frequency that you are going to get from the CTC mode is going to be equal to like this. So I would encourage you to put some values over here. So suppose you can use n is equal to 1, and suppose your input clock is 1 megahertz. Then suppose you count from 0 up to 100. So you have f output compare clock as equal to the input clock 1 megahertz divided by 2 multiplied by 1 multiplied by, let's say, suppose I want to count up to 99. So 99 plus 1 is 100. So this is actually 1000 into 10 to the power 3 divided by 200. So 5 kilohertz. So this is going to generate a frequency of 5 kilohertz. So this is a small numerical. Now, usually what what we do with this kind of equation is that if we want to generate a specific kind of specific frequency signal from the timer using the CTC mode, then all we need to do is we use this equation to actually find the value of OCR and X. So suppose that I want to generate a frequency of 10 kilohertz. Now there are two things that I can manipulate over here. So input clock is fixed again at, let's say, 1 megahertz. Now I can manipulate two things. I can manipulate n and I can manipulate the OCR and X. So suppose initially I take n is equal to 1. If that is the case, then 10 into 10 raised to the power 3 is equal to 10 raised to the power 6 divided by 2 multiplied by 1 multiplied by 1 plus OCR. So this is going to be equal to so 1 plus OCR is equal to 10 into 10 into 10 raised to the power 4 divided by 10 raised to the power 4 into 2. So I'm doing this simplification in a very childish manner just to show you how it works. So 2 and 2 5s are 10. So this is equal to 50. So OCR value is going to be 50 minus 1 is equal to 49. So if you drive the timer with a clock of 1 megahertz, you set the prescaler value to n is equal to 1, and then you have your output compare register value set to 49, then your output frequency is going to be 10 kilohertz. So you can expect a question like this, let's say, in the exam. Then you have the fast PWM mode. The fast pulse width modulator or the PWM mode, it is set whenever you have the waveform generator mode bits set to 0 cross 3 or 0 cross 7. So it provides a high frequency. That is why it is called fast. High frequency PWM waveform generation option. The fast PWM differs from other PWM option by its single slope operation. So this is something that we are going to see very shortly. The counter counts from bottom to top, then restarts from bottom. Or top is defined by as 0 cross FF whenever WGM 0 bits are set to 0 cross 3. And top is defined by the output compare register when these bits are set to 0 cross 7. Okay, so I think I misplaced this slide. Okay, so these are the slides which I have included just for those people who don't understand what is PWM, so they can go through this slide as well as this slide. So I'm not going to discuss them. I think I have discussed them for quite some time, a number of times in the previous lectures also, and in this lecture also. Okay, so let's discuss the fast PWM mode again. So in non-inverting compare output mode, the output compare 0 is cleared on the compare match between the timer control, the timer count, and the output compare register, and set at bottom. And in inverting compare output mode, the output is set on compare match is clear at bottom. So due to the single slope operation, the operating frequency at the fast PWM mode can be twice as high as the phase correct mode. How does it work? Let me show you. Okay, so in the fast PWM mode, the timer is counting from 0 up to the top value that you have set. At the top, it rolls over, comes back over here, and then it goes again, get back, and this is how it is functioning. So what is happening over here is, here you see that fast PWM has actually two different modes of operation, and one top is equal to 0 cross FF, which is 255, and then the top is given by the output compare register. Okay, so let's just take the first case. So what happens is that, so suppose that this is how you are working. So this is the top. Now what will happen is that your timer is going to start counting from 0 up to top. So it is counting from 0 up to top, nothing is happening. Then again counting from 0 up to top, nothing happening. So what happens is that if you set the output compare register to a certain value, then at that particular value, the output compare pin is going to toggle to 1 in the non-inverting mode, and it is going to toggle to 0 in the non-inverting mode, whereas it is going to toggle to 1 in the inverting mode. Okay, but the timer is still going to count all the way up to the top. So it goes to the top, and then again it rolls over to 0. It starts counting again, and now this time it let's say encounters the output compare register value has changed, and it arrives at over here. So you see that now again. So actually before this, once it hits the top, then it toggles again, and it goes from 0 to 1. So it keeps moving at 1 again, and then once again the output compare register and the timer value becomes equal. So then again it toggles to 0. It continues to 0 until it hits the top. At the top, it again goes to 1. And again, let's say here now the output compare register and the timer value become equal. Then here it again toggles to 0. So you see that in the non-inverting mode and inverting mode, the only difference is that the waveform is inverse of the other in the some case. So for example, in the inverting mode, the output is inverse, or the inverted version of the output in the non-inverting mode. But the output, how it is being generated, so I come again, that the timer is counting from 0 all the way up to the top. So as long as the output comparison has not occurred, the output compare pin remains at 1. However, as soon as output compare register value and the timer count value, they become equal, it jumps to 0. So as soon as you see that here the comparison occurs, the match occurs, so this output compare pin, which is running at high, it goes low. And the counter keeps counting, goes all the way up to top, and at the top, then again it goes to the bottom, right? So once it goes to the bottom, the timer rolls over. Then at that point, your output actually again goes from low to high. And then again, when the comparison occurs, it goes from high to low. And then once again, once it rolls over, it goes from low to high. So this is how the fast PWM mode is working, and it is called a single slope operation because you see that the timer is only moving from 0 to top and not from top to 0. So the last mode of operation is the phase correct PWM mode, and it again has two different variants. If the uh, we keep the pins, the wave generator mode pins to 01 or 05. Now, how does this operation operate? Let's discuss it. So first of all, the counter goes from bottom to max. In this case, the top value is not selected by the output control register. Now, in the normal inverting compare output mode, the output compare pin is cleared on the compare match between the timer count and the output control register. While in the upcounting the uh, and it is set on the compare match while the down counting. So first of all, instead of reading this text, let's look at the diagram. So first of all, the phase correct PWM mode is different from fast PWM mode because in this case you have up counting as well as down counting. So the counter starts from 0, goes all the way up to max, and then from max it goes all the way up to bottom 0. So here you can set the value of the output control register to different values wherever you want it, and however in this case the points at which these values are being set are when the counter reaches its max value. Now, the as long as the output control register output compare register value is set to max, then at that the output control pin is driven high. So if you set this output compare register value to max, which means 0 cross FF, then the comparison does occur, but the PWM is actually not generated, the output remains high. So basically what you're saying is that you have a PWM with 100% duty cycle. So for the entire duration of the pulse, your signal is at the high level. And if you set it to low, which means if you set it to bottom equal to 0, then the output compare pin value is driven continuously low. So first of all, this is the difference. Then what happens is that it compares the output compare register value and the timer count value on the up count as well as on the down count. So for example, suppose that at this point we have set the output compare register value to suppose 125. So this is the value 125. So the value is the output compare pin is being driven high. At this point on the down counting, so you set the value of output compare register to something different than max. So as soon as you do that, your output compare pin goes low. So it remains 1 as long as your output compare register value is set to max. But as soon as it is different than max or bottom, then your output is driven low on the down counting side. Now, so suppose the output compare register value that you set was 125. So once this value is compared, the timer counter count starts from 255, move downward, reaches 125. So once it reaches 125 on the down count, then the pulse goes high. It remains high uh, it counts from 125 to 0 and then even starts counting upwards. And once again, once it reaches 125, then at that point, 125, it again compares. The comparison is made between the timer count and the output compare register, and this time it is driven low. So this is how it keeps toggling. Now, the last few things about page correct PWM mode. The PWM waveform is generated by clearing or setting the OC0 register at compare match between the output compare register 0 value with the timer count 0 value. So when the counter increments and setting or clearing the OC0 register at compare match between OC0X and the timer count 0 when the counter decrements, right? So all it is saying is so when you are up counting or whenever you are down counting and your output compare register values are not set at the extreme values of bottom and backs, then what happens is that whenever a positive comparison occurs between the output compare register and the timer count, then the output compare pin actually toggles from 0 to 1 or 1 to 0. And the output compare pin, which is inverted, has the inverse of operation of this. So that's all for this lecture, and in the next lecture we are going to discuss how to actually use timer and PWM in Arduino. So in that we are going to actually see in what all ways can we configure timers, counters, PWM using the code and also simulation. So that is going to give us a more idea. So I know that this lecture was quite complex because there were so many things going on, but we are going to see this in action and see some practical examples, and that is going to clarify this thing. So because this is very important lecture, that's why I do not want that I should leave it here. We will take it forward from here by covering the code as well. Jazakallah.